And now, on to our opening keynote speaker, who will discuss the present and future of AI. David Cox is the IBM director of the MIT-IBM Watson AI Lab, a first-of-its-kind industry academic collaboration between IBM and MIT, focused on fundamental research in artificial intelligence. Prior to joining IBM, David was the John L. Loeb Associate Professor of the Natural Sciences and of Engineering and Applied Sciences at Harvard University, where he held appointments in computer science, the Department of Molecular and Cellular Biology, and the Center for Brain Science. He led the development of the Fundamentals of Neuroscience, one of Harvard's first massive open online courses, which has drawn over 750,000 students from around the world. Ladies and gentlemen, please welcome Dr. David Cox.
Great. Thank you for that kind introduction and for the walk-on music. That's great. I'm the director of the MIT-IBM Watson AI Lab. It turns out that the Watson isn't actually named after Rudy, but I did learn that Rudy has actually worked for IBM 30 times longer than I did. I just joined about a year ago. I'm a recovering academic. I've been at IBM for about a year. This is my first real job, so my mom's very happy that I finally got out of school. But I will say, having been an academic, I know how hard it is to chase technology, to chase knowledge. Hats off to you. You're teaching in one of the fastest moving fields on Earth, and perhaps even in history. So what I thought I'd do here today is give you a glimpse into what maybe the future looks like, to give you a little bit of a heads up. The lab I run is focused on fundamental advanced AI research. We're talking about artificial intelligence today, and actually my business card actually says artificial intelligence on it in 2 different places. But who's actually comfortable with the term artificial intelligence? I'm going to put my hand down. I would say as an academic, 2017 and before, the academic community, I was very uncomfortable with the term artificial intelligence. I would try and say machine learning, or be more specific and say deep learning. And then for whatever reason in 2018 and beyond, we all gave up, and now we're all calling it artificial intelligence. Google calls it artificial intelligence, IBM calls it artificial intelligence, academics call it artificial intelligence. But when I came to IBM, they had done something that I actually really liked, and I think it's helpful for framing the discussion around AI and where AI is going. They did something very simple. They just put adjectives in front of AI so we could be clear about what we're talking about when we're talking about it. And that's to distinguish on the left side of this slide what we have today, which is we call narrow AI. Now, it's very powerful AI, but it's fundamentally limited in important ways. So we want to sort of distinguish that also from, on the right side of the slide, general AI, which is what the press likes to talk about. It's what the public likes to talk about, systems that become conscious and Skynet and Terminator and all this stuff. Interesting philosophical debates, but we don't think we're anywhere close to that. In fact, you'll see at the bottom of the slide, when IBM Research came together and tried to decide when we think that era is going to actually arrive, they put on the bottom of the slide 2050 and beyond. And of course, when you ask scientists when something's going to happen and they tell you 2050 and beyond, that means we have no idea whatsoever, but it's no time soon, right? But in the middle, between narrow and broad and general, that's where we think the real opportunities are, and that's really what the lab is about, and this is what we call broad AI. So let's just unpack that a little bit. So why do we call today's AI narrow AI? And that's because it's fundamentally limited in that it's single task, single domain, one thing well. So this is exemplified by deep learning. So if you have many, many examples, thousands, millions of examples, carefully labeled, carefully curated in balanced ways, you can build a system that could potentially even have superhuman accuracy and superhuman speed for certain tasks. And I have a picture of a lesion, a skin lesion here. This is sort of the canonical example. If you have thousands or millions of examples of skin lesions, you have a doctor label them as cancer or no cancer, you can build a system that can do better than human doctors. And that's not surprising because the system's been trained on the equivalent of practicing medicine for hundreds of years, right? So in that narrow domain, you can do a lot. Meanwhile, generally on the other side, what we imagine in the future, cross-domain learning and reasoning, broad autonomy, something that can decide what it wants to do for itself. That's interesting to think about, but that's not where we are today. But where we're going is this broad AI. So multitask, multi-domain, being able to take knowledge from one place and apply it in another. Multimodal, being able to flexibly combine data from lots of different places. Images, video, audio, structured data, unstructured data, text, all together. It needs to be distributed, so it needs to be run in the cloud, but increasingly AI is going to also run at the edge and perhaps in our mobile devices or even in the sensors in sort of an IoT setting. And then interestingly, it needs to be explainable. So one of the things we see again and again is that IBM's customers, who are basically all of the largest companies in the world, know that an AI transformation is coming to their business, but that transformation is as much a people transformation as it is a technology transformation. So people are going to have to change the way they work, which means that the technology is going to have to meet them halfway. So it's not okay to have black box systems. We actually have to have systems that can explain themselves and interact with humans in human terms. So let's just motivate that why we aren't quite there today. So who's heard of deep learning? Just quick show of hands. Okay, that's good, because in 2015, Forbes said that deep learning was going to eat the world. And I think to a first approximation, we're on our way to that journey. Here's an example of the amazing things that deep learning can do. So this is from 2015, which is in AI terms a long time ago. This is a paper from Andrej Karpathy, who now leads Tesla's self-driving car program, and Fei-Fei Li, who's a professor at Stanford. And this is a system that can take an image and produce a beautiful, accurate, natural language caption. So you can look at that picture and say a man in a black shirt is playing guitar. Look at the other one and say construction worker in an orange safety vest is working on the road. And I think it's safe to say when I started my career in computer vision, I wasn't sure that we'd be able to do this in my entire career. I thought I might retire and never see this happening. So this is just a sign of how fast things are suddenly moving. Here, basically now there's not a game that humans are better at than machines. From Jeopardy, which we did in 2010, to AlphaGo beating the world champion in Go, to poker. Carnegie Mellon beat the poker champion. And IBM even created a system called Project Debater that can have a debate with you. So we even have machines that can argue with us now. So, and then it's not just that, right? It's even going into domains where we might not have expected computers and AI to go, even into creative domains. So here's an example of a system where, a style transfer system where you can take a photograph and then re-render it in the style of any artist you like. And this was back in 2015 on the left. And then on the right, this is the product of something called a GAN, a generative adversarial network. This is a very hot area of research today. None of those 4 pictures is a real thing. These are all figments of an AI's imagination, just completely imagined. So that bubble, that dog, those don't really exist in the real world. So this is just giving you a sense of just how amazing the capabilities of some of these deep learning systems are getting. But there's a problem. So does everyone know what this object is? What this picture is of? Who said a teddy bear? So this is actually what all of the state-of-the-art object recognition systems will say that this object is. So you go to Google, you go to IBM, doesn't matter. They're going to say teddy bear. In fact, this is a piece of art in the Museum of Modern Art in New York called Luncheon and Fur. And you can start to get a sense that maybe, even though deep learning is powerful, even though it's eating some parts of the world, there's something missing. It's getting fooled in important ways. These same images I showed you earlier of these images and these beautiful captions, if you take that very same system, you show it this image, it'll say something like a man riding a motorcycle on the beach. You show it this image, and it says an airplane is parked on the tarmac at an airport. Show it this image, and it's a group of people standing on top of a beach, which is true. Score 1 for the AI system. But you get a sense that even though these systems are amazing, even though they're doing tremendously powerful things, there's a sense in which they're not actually really extracting the real structure of what's there. And there's more to it than that also. So our systems today are trained on thousands and millions of examples. So big data. Why do we say big data? It's because all of our tools require big data to work. But your brains don't require big data to work. So who's seen this image before? Does anyone know what this is? Okay, great. So even though you've only seen this is a single example, not millions of examples, not even thousands of examples, one example. You're now experts in recognizing this object. So if I show you this, I can ask you, is the same object present? And say yes or no. Yes. I can answer questions like, how many are present in this image? 2. And is there one present in this image? Yeah, but it's weird, right? So we have a really sophisticated ability to work with small data, not just big data. And we are able to work with data in contexts that are different, that are corner cases that we haven't seen before. And this is really a magical ability. And it's so interesting, and this is not a sort of abstract thing. It turns out, does anyone know what AuntMini.com is? So this is actually the newsletter for the Radiologists Association. So doctors who look at x-rays have a website called AuntMini.com. So why would they have a website called AuntMini.com? It turns out it's an inside joke for radiologists where they'll say some things you'll see on an x-ray, and once you've seen it, you know it forever. It's like Aunt Minnie. It just looks like Aunt Minnie. You don't need to see lots of examples of it. So this notion of these very rare events that you see one of and you can work with, that's fundamental to so many fields of enterprise, so many fields of medicine, so many things that happen in government. And there's other problems with AI that we need to be aware of as well. So here's an example of a system where, again, this captioning system on top took that picture of a stop sign and then created the caption, a red stop sign sitting on the side of a road, which is a beautiful caption for that image. However, my colleague Pinyu Chen at IBM subtly perturbed that image. So just changed a few pixels here and there. So small changes that, in fact, I would argue that none of us can actually see what's changed. Those two images at the top and the bottom look identical to us, but to that AI system which produced the caption, it actually now produces the caption, a brown teddy bear laying on top of a bed, with high confidence. So we're into a new era where every system that's ever been built by mankind can be hacked by mankind. AI is no different. So now we're into this weird and wonderful and strange world of AI hacking, and we don't understand why these attacks work, and we're going to have to figure out how to beat them. So this really is then the roadmap for what we're doing at the lab that I run, asking what is the path to broad AI? We need systems that are explainable. It's not okay to have black box systems. If the system makes the right answer, we also need to understand why it made that decision. If a system makes a mistake, we have to understand how we go in and fix that error. The systems have to be secure, so we have to be able to trust that when we deploy these systems that bad actors can't come and do attacks like the one I just showed you. You could imagine in a self-driving car context that could be problematic if your car suddenly decides that a stop sign is a teddy bear. I'm glad that the Secretary mentioned ethics. Ethics is actually core to everything we're doing. For humans to trust and accept and get the full value out of AI systems, and for AI systems to work for us, we need to embed ethics and fairness into our data, into everything we do, and you know, actually having systems that are fair is not a trivial thing, and it's something we need to increasingly pay more attention to. And then at a practical level, we also, even though this is maybe a little bit heretical to be at a conference that has big data as the first two words in the name of the conference, I would argue that actually we need to focus more on small data. Again, because so many problems in enterprise actually are driven by small amounts of data. We can work with it because we have human intuition and we have this incredible ability to process with small data. And that includes a couple different parts. Learning to transfer, so transferring what we know from one domain to another. You know, my daughter didn't need to look at flashcards of thousands of pictures of dogs and cats before she knew what dogs and cats were. Just like that antenna that I showed you, she was able to see a single example and then get it. We need machines to be able to do the same thing. And then we also need to be able to reason about data. So be able to extrapolate beyond, to be able to, you know, the antenna that was on the stock of a gun, that's for shooting down drones, by the way. That you need to be able to reason about things in context you haven't seen them before. And then finally, the last piece that we're working on is infrastructure. So computing each year increases in the amount of power it uses. So each year we're just using more and more power. And it turns out that by some estimates, if computing keeps on its current track, by the year 2040, we'll exceed the power budget of the planet Earth with computing. So there won't be enough solar radiation coming from the sun, not enough stuff we can dig and pump out of the earth and burn to actually keep up with our computing habit. And that's even leaving aside Bitcoin. And AI is one of the heaviest and most power-intensive workloads that we have. So we're working on ways of new computing architectures to make drastically lower power AI, using things like analog computing, where we think we can reduce the power consumption by a factor of 100 or 1,000 for traditional deep learning workloads. And then we're also working separately on quantum computing. So IBM's a leader in quantum computing. We built the first commercially available quantum computer called the System 1. And we're asking how quantum and AI might interact with each other. Nobody knows. We just don't know whether those will impact each other. But quantum is so new and so different that we have to put down chips to ask those questions. So to do this, IBM decided to tackle this issue of broad AI. We needed a partner, and we chose a partner in academia, because academia and industry have a natural affinity for each other. So you know, IBM is one of the last, so I'm part of IBM Research, even though it says Watson in the name of my lab. We're actually part of IBM Research, not the business unit that's called Watson. We're one of the last remaining industrial research labs from the Bell Labs era. We have about 5,000 people globally, sort of the size of a medium-sized university. And we have Nobel Prize winners, we have Turing Award winners, we have National Academy of Engineering members, together with MIT, which needs no introduction. It's one of the great engineering universities. And we're partnering together around AI. And it's interesting, actually, IBM and MIT have been partnering around AI literally since the beginning of AI. So it turns out the term AI was coined in 1956 at a workshop at Dartmouth. Can you imagine in 1956 imagining that all of this would happen today, so many years later? And it turns out this workshop was organized by IBMers, so the two guys in the back. You can tell the IBMers because they're wearing ties. So Nathaniel Rochester, who built the IBM 701, which was one of the first practical computers, together with future iconic MIT professors in the back, Marvin Minsky, on the right, Claude Shannon, who's the father of information theory. They came together and they dreamed up this future of artificial intelligence. And that partnership makes a lot of sense, and I think it's essential because academia has these long-range time horizons, perhaps 100-year time horizons for knowledge, bringing together all departments of different, chemistry, biology, economics, physics, together with IBM, where we are big enough and where we are academic enough that we have some of these basic science departments, but critically we have industry problems, we get to see our customers' data, and we have the compute resources increasingly to be able to tackle these problems. And one of the major problems that's emerging today in AI research is universities increasingly can't even reproduce results that are being produced by industrial labs simply because they don't have enough compute power to do so. So IBM, we're the company that built Summit and Sierra, which are the largest and the second largest supercomputers in the world. We can bring that expertise to bear to make our MIT friends more effective. So by the numbers, IBM is investing $250 million in this lab. It funds roughly 100 people, working on roughly 50 projects. And we have a 10-year time horizon for what we're doing. So imagine even just 6 years ago, deep learning wasn't really on the radar yet. So this is a very long commitment that we're pursuing. So what are we actually working on then? So I'm just going to give you, I could tell you, I could talk all day. I was an academic, I was a professor, so I could literally talk all day if you let me. But what I'm going to do instead is I'm going to talk for just a little bit about just a few glimpses of what's coming in the next few years and what's coming a little bit longer, farther out, to give you a heads up as you're thinking about how you educate towards these fields. So one thing that we mentioned earlier that's so important is explaining, understanding how neural networks work, understanding how these systems work on big data, because we need to be able to trust those decisions. Trust is such an important part of deploying a new technology. So one thing that we're doing is we're building AI debuggers. So this is a major research initiative within the lab. Back when I learned about computer science, when I was starting on computer science in the 1990s, people said that software would eat the world. And now people are starting to say that AI is going to eat software. And I think they're right. I think we're going to increasingly replace traditional software systems with data-driven AI-based systems. Now, the thing that's mildly terrifying about that is that back in the 90s, we at least had debuggers. And today for AI, we don't really have a notion of a debugger. So if something's broken, we don't know what to do. So here's a case of something broken. Here's a system, again, a captioning system like what we saw earlier, where the AI system looked at that picture and said washing dishes. Okay, why did it say washing dishes? It should have said brushing teeth, because it's a cute little girl and she's on the ledge and she's brushing her teeth. Now in a traditional AI workflow, it's not clear what you do next. Do you throw away all the data? Do you start over? Is the model wrong? Is the data wrong? What's going on? So with this team, and again, all of our projects we have an interesting model where all of our projects are jointly conceived and jointly executed by MIT faculty, students, and postdocs, and IBM researchers. So you'll always see at least two people on these slides, an MIT project lead and an IBM project lead. We work together on these projects. This team is asking, how would we build a debugger that could actually helpfully guide us in fixing a system that's broken? And here's what they've done. So this is a system that's taken, basically can do two things. It can project back to the input and understand which parts of the input gave rise to the activity of an individual neuron in the neural network, or unit in the neural network. And can also project forward to an intermediate label to sort of ask, what concept is this neuron representing? And it's sort of an open question what neural networks know and what internally they understand. Even the question of what is understanding is complicated. But we can at least ask, how is this neuron, what does it fire for? What is it active for? And what you can see is neuron 1679, just an arbitrary neuron out of the network, looked at those parts of the image and voted for bathroom. So that neuron, for all intents and purposes, is not, in some sense representing the concept of a bathroom. The next neuron was representing the concept of a kitchen, and it was active. Okay, well there's a sign of part of what was going wrong. It's not an unreasonable thing that it looked at those cabinets. Kitchens also have cabinets. You can kind of see why it might have made that mistake. The next one said house, that's good. Next one said bathroom, that's good. Next one said person, there's nothing wrong with that. But the interesting thing is you can, by having these tools to actually look inside the black box and interrogate, we can see that none of the neurons detected the toothbrush. And this is actually probably a pretty important reason why this network failed. So now you actually, rather than just having sort of a sense that the thing was broken and not knowing what to do with it, now you actually have an action item. We need to enrich the data set with toothbrushes if we want to have it see the toothbrush. Maybe that toothbrush is too small. Maybe the sort of effective visual resolution of the network was too small to be able to see the toothbrush. So we can start to get a little bit of a foothold and start thinking about how can we debug these systems and not just treat them like black boxes. And of course, that's an example in vision, but you can apply the same thinking and build a suite of tools for lots of different applications. So this is an example of a translation system. This is called a sequence-to-sequence model. It's translating from German to English. That system has made a mistake and made the wrong German translation. And what you see here is a tool that was built by Hendrik Strobelt, who's one of our researchers in Cambridge, where you can actually reach inside the neural network and manipulate and say, well, what if the network had deployed its attention this way? What if it had made this translation instead of that translation? And that sort of counterfactual reasoning and playing with the system is what it takes for a programmer in traditional systems to debug a system. And that's the kind of thing that we need, and that's the kind of thing we're building for building AI systems that are correct and debugged. Another area that's really important is extending the technologies we have today. So there are serious problems and limitations of what we have. We'd like to be able to extend and be able to work with less data. And we have a couple projects in this area. One area that's really important, oftentimes when companies have big data or governments have big data, the big data isn't the problem. The problem is they don't have big labels to go with the data. So it actually takes quite a bit of effort to curate, get clean labels on that data. And what you'd like to be able to do, and then the problem is that none of that data is stationary. That usually what happens is the data is changing over time, the landscape is changing, and even when you do all the effort to train a system and to curate all that data, you wait a few years and the data's changed. So wouldn't it be great if we had a way to take what data we have that's got labels and figure out how to apply it to new data? So we don't have to go through that process again and again and again. So this is an example of a project we're working on about doing more with less annotation. So you can imagine if you had a system that was trained to recognize handwritten digits, could you transfer the knowledge about those handwritten digits to street sign numbers? It's the same content, they're numbers, but it turns out today's AI systems, you train them on handwritten digits, they'll do terribly. They won't do anything at all with street sign numbers. So this team has built one of the state-of-the-art methods for transfer learning in this context. The images on the right are examples of mammograms. So it turns out that mammography technology has been changing over time. So the image on the left is a film mammogram, where they actually shot an X-ray film. The one on the right is a digital mammogram. They took it out the digital sensor. It turns out that human doctors are way better at detecting cancers in digital mammograms than they were in film mammograms. But they didn't have to go back to medical school to do that. They just instantly knew what to do. AI systems, it turns out, if you train them even on one vendor's mammogram system and then try and transfer it to a different vendor's mammogram system with the same technology, it doesn't work very well. So our AI systems need to be able to transfer better, and this is a really important thing that we're working towards. Okay, what's coming in the next 3 to 5 years then? So there's a whole host of things where our AI systems aren't sort of yet living up to AI. So one of the reasons we were so uncomfortable with artificial intelligence is a lot of these systems are basically function approximators. They take some input and they produce some labels, they produce some output. We want to be able to have systems that can more flexibly reason about the data they're looking at. So here's an example of some questions that neural networks actually have quite a bit of trouble answering. Things like how many blocks are on the right of the 3-level tower? Will the block tower fall if the top block is removed? What is the shape of the object closest to the large cylinder? These are questions that even a child could answer, but our current deep learning systems actually struggle quite a bit with these issues. So this is an example of a program that we're working on. It's actually a major initiative within the lab to combine neural networks with symbolic AI systems to actually be able to more flexibly reason about data. And I'll just skip ahead and show you one example of a system where we're taking neural networks, which are the sort of the new hot thing in AI, but which has actually been around for a long time. So back in the 1980s, we had the sort of the rudimentary, all the basic ideas of neural networks. And really what they were waiting for was enough data and enough compute to come along to make them really work. There was another kind of AI at the same time called symbolic AI. It was able to logically reason about symbols and objects and those kinds of things. And it really hasn't enjoyed a resurgence the same way. And what this project is doing is asking, now that we have neural networks, can we combine them with these other old ideas of symbolic AI, make something that's more than the sum of its parts? So we're combining neural networks that can see and language networks that can understand natural language processing. But instead of just using them directly with each other, we can use the vision to create a structured symbolic representation of the world, and we can use the language to actually create a symbolic program, which we then can operate on the symbolic structured representation. And we can train the whole thing together with reinforcement learning to build systems that can actually genuinely flexibly reason and not just produce outputs that we don't understand. And this is actually a research program that's been producing some of the top papers and top conferences lately. There's a data set called Clever, which is created specifically to be difficult for working with neural networks. And basically, by using these symbolic hybrid methods, we've been able to get effectively perfect performance on this task. So this is something we're really excited about that's going to be moving forward over the next few years. Another area that we're very excited about is causal inference. So one of the problems with our current machine learning methods today is that they're largely correlational. One of the problems with correlations is something like this. So here's the divorce rate in Maine, plotted in red, and the per capita consumption of margarine, plotted in black. I think the relationship is self-explanatory. Of course, this isn't real. There's no relationship between the divorce rate in Maine and the consumption of margarine. This is an example of a spurious correlation. There's actually a website at the bottom that collects these spurious correlations. And here's another example of something that can go wrong with purely correlational methods like what we have. The British Medical Journal asked the question, is caviar a risk factor for being a millionaire? And it turns out it is. It also turns out that caviar is associated with better health. People who eat caviar have better health. So clearly we should go out and give caviar to everyone so they'll be healthier. No, it's the wrong inference. So the issue is that people who have money can afford caviar, people who have money can also afford good healthcare, and so there's a latent confounding variable. So causal inference is a new field of machine learning, which is emerging now and will be hopefully in your classrooms in the next 5 years, about understanding cause and effect, to be able to infer a potential causal structure from observational data, to be able to then test. There's really no way to get causal structure without actually doing interventions and testing, and then being able to, once you have that causal structure, make better decisions. And particularly in government, there was a case in Florida where machine learning was being rolled out to decide parole, to make parole decisions and predict recidivism, and that's a terrible idea. That's a catastrophically bad idea because you basically launder all of the biases in society through an algorithm and make it seem unbiased, but in fact you're just taking the biases of society and recapitulating them. So there's a new effort, particularly led at MIT, to be able to bring causal inference methods so that we can be very clear that we can factor out causes like race that we don't want in the data. So that's just a glimpse of what we're working on. This is sort of the battleground. I think if we're successful, and I hope we are successful, these will be some of the topics that will sort of begin to show up in your curricula and perhaps even dominate your curricula. And I think the potential is really excited, and I'm really excited that you're all here today and that I can share this with you. Thank you.
Dr. Cox has agreed to take a few questions, so if you have a question, please come to the microphone and state your name, and please keep your question brief. Don't be shy.
Perfectly self-explanatory.
Here's one. We have a question here.
Yes, hello, I'm Barbara Lucas-Johnson from the University of Connecticut, and we've been utilizing some of IBM software, Watson and SPSS Analytics, and I just wanted to find out, like, what's the evolution, because as we utilize the tool, particularly Watson, like the application of it still seems kind of fuzzy, and some of the answers that you get don't seem logical, so I'm just thinking, like, how do you kind of take the next step and make that interpretable for businesses and for students and the whole world?
Yeah, that's a great question. So Watson, we should clarify what Watson actually is. I mean, first and foremost, Watson is a person, not just Rudy, but also Thomas J. Watson, who was the founder of IBM. So for whatever reason, IBM, it really started as a joke, because like the research center in New York is called Watson, was called Watson, T.J. Watson Research Center, and they named the Jeopardy robot thing that, and then that became the name of a business unit. So what Watson basically is a brand that they attach to anything that's AI related that IBM gives out. So The stuff that we're working on is destined for eventually becoming the Watson product, but we're a little bit longer horizon. So as we build technologies for better explainability, they gradually find their way into the product. And basically what Watson is today is sort of a relatively easy to use API for using standard machine learning type tools and some basic AI tools and visual recognition and things like that. And we do hackathons with MIT, with undergraduate students, and we find that it's a nice level where people can very quickly get up and running and do some AI stuff. That said, in the real world, when we deploy some of these AI systems in the world, you have problems like the ones I showed you. Like they're not yet, nobody's systems, not Google's, not ours, not anybody's, are really understanding always what the system's understanding what they look at. And I'm personifying the systems a little bit, so forgive me for that, but there's a sense in which they're not carving at the right joints, and sometimes they'll make funny mistakes. So really what Watson is, I think in an educational context, is it's a low barrier to entry way to get access to some tools. And those tools will evolve over time and will get better. And IBM Research, where I work, are the people who are sort of trying to feed that into that system. Okay.
Anyone else?
Hi, I'm Ellen Fleming. I'm from the University of Maryland in College Park. My question to you is, you talked about building debuggers, but isn't it also important to build tools to tell you if you're getting bad results? Because otherwise you're forced to examine these things and know whether this is truly good or not. So in addition to debuggers, what are you doing to build things that can tell you rightness of these models?
That's a fantastic question. So AI is actually really hard to deploy in the enterprise today. And this is something IBM actually cares a lot about. So how do you deploy AI at scale? And a big part of that is being able to do quality assurance, be able to do automatic checking of vulnerabilities. So IBM actually has a product. Again, this is actually something that came out of research and moved into product, to give you an idea of that sort of life cycle, called AI Fairness 360 and AI OpenScale, where it's a system. AI OpenScale is a system for deploying AI models, where you can deploy models, redeploy them, QA them. You can assess them for fairness. Actually, it turns out there are more than 20 definitions of fairness, and we've basically created the algorithms for all 20 of those definitions, 20 plus of those definitions, automatically run them on your models as a matter of course, right? Because you're going to constantly adding new data, you're going to be redeploying the model. Is it still fair? Has bias snuck in? You want to be able to have an automated workflow for doing that. Same thing for security. So increasingly, they're called adversarial attacks, where you change a few pixels and it fools the AI system. You'd like to be able to automatically assess how vulnerable you are to those, and then ideally even retrain the models so that they're secure against them. So I think increasingly we're going to see, as AI matures, and as we really try and deploy these things in real world settings in governments and companies, we're going to have to see these kind of tools that automatically give you a sense of how you're doing. So that's a very important part in the development, because there's no shortage of people building proofs of concept out there in industry, but then actually having the frameworks to automatically, sort of like in traditional IT, people call it DevOps. We're thinking in terms now of model ops or AI ops. Like what is the discipline? What's the workflow look like? And I think that's incredibly important. Again, because at the end of the day, it's about trust, and you need to be able to constantly be monitoring things. These things will be changing, particularly if they're data driven. So that's definitely high on our radar.
We have time for one more question.
Hi, good morning. I'm Alan Drimmer, Chief Academic Officer here.
Mm-hmm.
Thank you very much for your presentation, which talked a lot about some of the cutting-edge research that you're doing and positioned the field broadly. Not to be a wet blanket, but some of the things that I've been seeing also talk about the darker side of AI
Mm-hmm.
and some of the dangers associated with it. You see it, in popular culture with movies, even actually as far back as probably 2001: A Space Odyssey,
Mm-hmm.
Ex Machina, and
Mm-hmm.
things like that. But then Bruce Schneier, in a more serious way, and others have written
Mm-hmm.
about really some of the policy implications. I know that's not the focus of your talk today, but could you say a few words about that, how you think about it, and how researchers in general in this field see that?
Yeah, that's a fantastic question. So there's enormous responsibility. I mean, the responsibility that comes with doing this work, and policymakers absolutely have to be engaged in this all of these technologies in a deep and technical way, and they need to look to the academic community and in industry to give them that guidance. Is at the end of the day, of course, these technologies can be used in bad ways. So one thing you might worry about is job displacement. So there's a version of this where AI increasingly takes jobs away, and we'd like to not have that future. We'd like to have a future where AI, changes the jobs we do, that it enriches us. It makes it, it sort of makes us able to do things we weren't able to do before. But in many ways, these are choices, right? We need to legislate. We need to direct the technology in directions where the technologies will work for us and not against us. Certainly, AI technologies have the potential to be used to take away our privacy and take away our liberties. And we're seeing that experiment played out today with some of our national adversaries, China in particular, where today where big data rules machine learning, nobody has bigger data than China because they can aggregate all kinds of information because the norms around privacy are just different than what we have. So I think efforts to legislate and make sure that we're using the technology in ways that enrich us ultimately will fall to policymakers. Industry will have to self-regulate as much as possible so that we bring solutions to the table when we talk to governments. And I talk to the US government, I talk to the EU Parliament. There's a lot of interest, but we need to come to the table with those issues to educate. We need to come with solutions that are brewing. It's a very tricky thing. So GDPR was mentioned earlier. GDPR is an interesting case where they wanted to make systems that run on data be fair. So they said, well, let's just blind those. We're going to require that you don't collect the data on protected variables like race. It turns out if you want to be fair with respect to race, that's the worst possible thing you could do because the information about race is tied up in all the other demographic variables. So you took it away, you just took away the only tool we had to be able to factor it out, right? So that's a case where it's great that governments are getting out there in front and they're protecting privacy, they're taking a strong stance, but there also needs to be a little bit of a dialogue with practitioners to be able to understand and make sure that we're doing the right steps. So there isn't an easy answer to this. It will be a disruptive technology, but I think if we get together and we all work together, and I think academia and the educational system is absolutely a pillar of that discussion, then I think we can navigate this in a way that's going to be positive for humanity. Great. Thank you.